And the third type of equation is hyperbolic equation. We had partial u, partial t plus big U times partial u, partial x is equal to 0. And before I even use the Fourier analysis, can we just look from the solution we have seen before? What is the domain of influence? If I have a domain like this, okay, if I suddenly change, if I put a small perturbation on the initial condition here, what do you think is the domain of influence?
Local.
It's local in what sense? It's local in space, in time, or yes? Yeah, yes?
In space.
In space. Why? Can we also still use the principle of linear superposition? Do you have any explanation?
Well, I mean, just intuitively, I guess it's going to be simply a cone of influence because your initial perturbation is just moved around.
Okay, you must have studied the PDs before because because you gave a very good answer. In this case, if I look at the solution, if I use the principle of superposition, the influence of a perturbation is again like the influence of a very local initial condition, right? If I give a very local initial condition, the solution just keeps moving towards the right, right? Okay, so basically, yes, the effect is local. It's local within that spike. But in this space-time plot, I mean, this is basically, if you look at t keeps moving, right? T keeps increasing. In the space-time plot, what is actually this spike? The spike is local in space for any given time. But in the space-time plot, what will it be? A line, right? Basically, we see this propagates towards the right. For any t, we take a cross-section, we are going to see this narrow region is a spike. But in the space-time plot, we are going to see, okay, this moves towards the right, it wraps around from the left boundary and comes here. The domain of influence in this case is a very narrow band that moves at a fixed speed. So for this type of equations, we call it hyperbolic equations. And this is the simplest one, where the domain of influence really is in a narrow band that doesn't even increase in the width. For general hyperbolic equations, you may get a cone, right, as somebody here has said. But the common feature is that influence does not spread instantaneously. They travel at fixed speed. It's like the speed of light, where if you change anything here, somewhere else won't even be felt after a certain time. I mean, it's better to think of a speed of sound, I guess. If you can only communicate via sound, then if you shout something, somebody far away won't even be heard after a little bit. All right. Okay. So why does the solution travel towards the right at a fixed speed? That can be seen from its Fourier analysis. Again, we set u at x, t equal to 0 as u0 of x. And we do the Fourier expansion of u, x, and t is equal to summation k goes from minus infinity to infinity u hat of k, which is again a function of time, times e to the jkx. Okay, and the first derivative term is exactly the same as the parabolic equation case. So we get d hat of u dt. What's different is instead of twice derivative, we have a single derivative. And u hat is still the same, but we have a jk instead of a minus k squared, right? Okay, so this term plus a big U times this term has to equal to 0. So the individual terms inside the Fourier series has to match. And if you match it, what you get is the time derivative plus big U times jk. U hat of k equal to 0. Can somebody tell me the behavior of this ordinary differential equation? Oscillatory, right. We have a purely imaginary multiplier here. Right, so for this equation, for this ordinary differential equation, if this term has a positive real component, the solution grows. If it has a negative real component, the solution decays. If it has a pure imaginary, the solution never decays, never grows. That is true for all the case, right? Except the larger the k is, the faster the oscillation is. So what you see when we see a spike moving towards the right is basically a superposition of many oscillations. The faster frequencies oscillates faster, and the overall effect is actually the spike or the solution traveling towards the right. All right, you can convince yourself by looking at every pair of solutions. If you take a k and minus k, you look at the effect of these summed up each other, which should only give you a real component. You're going to see it'll travel at a speed of exactly u. Okay, no matter what frequency it is, having an oscillation that is proportional to k is going to let that frequency travel at a speed of u. All right, so that's the hyperbolic equation.